Hello, students. Professor Gray here. We are in the middle of chapter 2, and we need to talk about the periodic table. So, in the 1700s, chemists were trying to identify and organize new elements, but there wasn't really a common way to do this. And in the 1860s, along came this Russian chemist named Dmitri Mendeleev. Now, this is not Mendel. This is not the monk who did the study on peas, whether they were green or yellow or smooth or wrinkled. That's not the same guy as this. This is Mendeleev. And in the 1860s, what he did is he arranged the elements in horizontal rows, and these rows had the atomic weight of the atoms increasing as they went across the rows. So if we take a look at a very rudimentary periodic table, you can see that as we go across this row, our atomic masses are increasing. And he would start a new row whenever he noticed that he needed to put an element under another one because they had similar characteristics. And you can see here we've got lithium, sodium, and potassium in the same group right there, and they do indeed have similar physical and chemical characteristics, and we'll talk about these characteristics a little bit later in the lecture. Okay, so what he also did that's really important is right here. He left spaces open for elements that he thought would be discovered. And if we look at this periodic table right here, what we'll notice is that we have zinc right here, and next to it is an open space that was predicted to have an atomic mass of about 68. And indeed it did. That was the first element that was discovered after Mendeleev put together this periodic table with missing spots. And this one right here is gallium. And that was discovered in 1875. And if we take a look at the updated periodic table right here, we can see that indeed zinc and gallium are next to each other. Now, if you take a look at the key up here, you'll notice that it tells you when the different elements were discovered, and you're going to need to know the year for every element on the periodic table, the year that it was discovered. Totally kidding there, don't freak out. This is just a fun little periodic table to look at to see which elements were discovered when. All right, so moving on to the next slide. This is also another one of those fun FYI types of slides that just shows you which countries each of the elements was discovered in. There are quite a few of them you can see here and here that says they were known to the ancients. So stuff like copper and iron and sulfur, those have been known for quite a long time. And look down here, yay, America, right? And that's followed up by a lot of German discoveries right there, a lot of British ones too. And then we go on to this next slide right here that talks about the horizontal rows. And today we call those periods. So you can see that we've got the first period here, second period, third period, and so on. Now, going left to right across the periods, you're going to have an increase in atomic mass, and that's how Dmitri Mendeleev set it up. And that is indeed what happens, okay? Now, the vertical rows, those are groups, or they're also called families. Now, what we'll notice is we've got 1A and 2A right here, and then all of a sudden it switches to B's. and it goes 3B, 4B, and then all of a sudden over here at the end we've got 1B and 2B, and that looks really weird. And then all of a sudden we've got the A's over here again, so it's kind of like, what's going on? And what you'll notice is different periodic tables will have different labels for our groups, but they tend to look pretty similar in that we have these first two groups over here, and we have these 6 groups over here that are called the main group elements. So you'll notice that both of those have A's after the numbers. And then the elements in the center, those are labeled with B's. Those are our transition metals. And what you'll also notice is that along with being labeled 1A and 2A, and those are just put in Roman numerals instead of the 1 and the 2. You have the I and the II. Don't worry about that. What we're looking at here is the fact that it goes 1, 2, 3, 4, all the way to 18. With how this is labeled on the top. And that's another way that the groups are labeled on periodic tables. So sometimes we have the A's and the B's, and then sometimes it's just labeled 1 through 18 all the way across. You'll see both of those. It just kind of depends on your professor or your textbook or how the periodic table is labeled, okay? Now let's talk about classification of the different elements in our periodic table. Now we're going to classify our different elements by physical properties first, and then we'll go on to classify them based on electronic properties. But I just want to review with you guys really quickly what a physical property is. Now, this is a property that we can observe without changing the composition of the matter. So you have the same compound before and after. So it would be something like melting point or boiling point. So in order to figure out that the boiling point of water is 100 degrees Celsius, you would go ahead and boil it and have a thermometer and look for the temperature that it boils, but you have H2O before and after the change. It's just that the H2O before is in liquid form and the H2O after is in gas form. So some other physical properties are color, odor, density, solubility, electrical conductivity, those types of things. Okay, so you have the same thing before and after the change. All right, so over here on this side of the periodic table, we've got our metals. Now, hydrogen is over here on the metal side because it has a lot of the same properties as the other elements in that same group, but it is indeed a non-metal. So you can see that it's got that green color for its box. And then the rest of the non-metals, they're over here on the right-hand side of the periodic table. So we've got oxygen, nitrogen, chlorine. Those are obviously not metals. That's pretty simple for us to make that assumption right there. And then in between the metals and the non-metals, we have elements that have properties that are in between the properties of metals and non-metals, and those are metalloids, and they are right here. So they're along the stair step right here that is dividing the metals and the non-metals. They're on either side of it right there. So one of our metalloids that you've probably heard about is silicon. Now, silicon is not silicone. Silicon you have heard of in terms of computers and anything that needs a semiconductor. Now, metals tend to be conductors and non-metals non-conductors, so it makes sense that metalloids would be semiconductors, okay, somewhere with properties in between those of metals and non-metals. All right. Now, specifically metals, these tend to be shiny and they like to conduct electricity, and they tend to be ductile, which means that they can be drawn into wires. And one of the elements that we do this with is right here. It's copper. We like to use copper in our wires to conduct electricity because it's good at doing that. We wouldn't put oxygen or nitrogen or sulfur in our wires because that wouldn't really power us very well. Metals also tend to be malleable, means shapeable. So if you think of grabbing a metal spoon from your kitchen and bending it, it's malleable. They tend to have high melting points and boiling points. So MP and BP, that's melting point and boiling point. So it goes from a solid to a liquid. It melts at a very high temperature. And it goes from a liquid to a gas at an even higher temperature. So because these have high melting points, that's the temperature where they go from solid to liquid, they tend to be solid at room temperature because room temperature is too low of a temperature to cause metals to melt. And that's really good for us because we like our metals to stay solid. Now, the exception to this is mercury. So Hg is mercury. That is our liquid metal. Moving on to nonmetals. These don't conduct electricity very well. So like we said, you wouldn't put nitrogen or sulfur in wires and expect to charge your phone. They're not very ductile, don't put them in wires, and they tend to be really brittle, and they have low melting points and low boiling points compared to our metals. And again, that's in general. So if they melt, which is going from solid to liquid at a low temperature, and they boil at a low temperature, that means they're in the gaseous state a lot of times at room temperature. And if you think about nitrogen or helium or oxygen, that will make sense. Okay, so at the bottom it says many are gases at room temperature because they boiled at a temperature that we would consider cold. All right, so that doesn't usually make sense to our brains because when we think of boiling, we usually think of water. But when something goes from a liquid to a gas, it's boiling. Even if it's boiling at minus 20 degrees, it's boiling, okay? All right, so metalloids, like we said, these are elements that have properties that are in between metals and nonmetals. And the example that we used was silicon. And this right here is silicon. So you can see that is definitely different from silicone, which is silicon spelled with an E on the end. So silicone is something that we use for implants in the body, so to make some part of our body bigger. All right, if we made implants out of silicon, that would be very painful. So the elements that we consider metalloids, boron, silicon, germanium, not geranium, that's a flower, germanium, arsenic, antimony, tellurium, polonium, and astatine. Now, polonium and astatine are in italics there because sometimes they're grouped with the metalloids and sometimes they're not. And let me go back to the periodic table here where we had metalloids. So here we have polonium and astatine. And on this periodic table, polonium is not included and astatine is, and that's just kind of gonna depend on whoever's making the periodic table or whoever is grouping the metalloids together. The elements at the bottom of the periodic table are heavy, and the heavier your element gets, the more unique its properties are in general. So if we're talking about metalloids and the specific property that we're talking about matches up with the properties of polonium or astatine, those will be included, and if they don't, they'll be excluded. Just know that sometimes those two are included and sometimes they're not, okay? Now let's classify our atoms by their electronic properties. So if we're classifying things by electronic properties, this means what are the electrons doing? So electrons in this class, I'm going to symbolize with a little e and a minus symbol, okay? So what are our electrons doing? How many electrons do we have? How many are in the outer shell of our electron cloud, etc., etc., because the electrons in our atoms are going to dictate what kind of reactions that our elements are going to want to do. So remember before we talked about the A's and the B's. Now again, the columns or the groups or the families that have the A's by them, the first two and the last six that are in yellow on this periodic table, are called the main group elements. And they're grouped together with those A's, or called main group elements, because they tend to have similar electronic properties and they tend to do things that we can predict easily. Now, the transition metals in the center, the ones that are labeled with the B next to their number, those tend to have really interesting chemistry. And if you go on to be a chemist and you take a class called inorganic chemistry, you get to talk about the transition metals, the chemistry of transition metals, all semester or all quarter long. And that's actually a really interesting class. But anyways, going on, let's talk about the first group. So group 1 or 1A, this is this one right here. Those are called the alkali metals. Now, alkali is also called alkaline sometimes. And alkaline is the same thing as saying basic, which is the opposite of acidic, and that would make sense that these elements are going to create a basic solution when they're put in water. So these are soft, shiny metals, and they conduct heat and electricity, and they also react violently with water. Now, if we look over here at this picture, you can see that sodium right there is being cut with a knife. So you can see that it's soft. When we think of sodium, we're thinking of sodium chloride usually, and that is regular table salt. It's the salt that we cook with. That is a compound of sodium and a version of chlorine called chloride, and the difference between chlorine and chloride we'll talk about in the next chapter. But over here you can see if you just have sodium by itself, it's that soft, shiny metal. Now, why do you think that person is wearing a glove while they're touching that metal? Well, sodium reacts violently with water, and there's water on your hands. So just think about if you've got sweaty palms and you put it on a piece of sodium, that might not feel really good if the water on your hand's going to react violently with the sodium. And this is what happens when you throw a little piece of sodium into some water, which is what all good chemistry graduate students do when they get to the lab. They get a tiny little piece of sodium and they throw it in these big deep sinks that we have in the lab, and it goes bzzz around the sink, and it's great fun for nerdy chemistry folks like me. All right, so what happens is that you throw your sodium into some water. So we'll put H2O liquid. And what's going to happen is, let me write my waters a different way. Let me write them as HOH instead of H2O. And what happens is the sodium comes over here and says, give me that NaOH. And this happens. And that AQ in the parentheses means aqueous, so it's saying that that NaOH is dissolved in water. And this fancy looking E right here is actually an L, meaning liquid, so the water is a liquid. And the S means what? The S means that's solid sodium. So this is aqueous. aqueous. There we go. Okay, I had a brain fart for a second. Okay. Excuse me. So the sodium comes and it takes the hydroxide, which is the OH, and then that leaves a hydrogen behind. But hydrogens don't like to be on their own. They like to be in a diatomic molecule. They like to meet another hydrogen and get together and form H2. Now, H2 is just two hydrogens that are bonded by a single bond. But again, hydrogens don't like to be on their own. They like to be in that little molecule right there. And that is a gas. So that's why I drew two waters over there. So that means that I need to put a 2 here because I need 2 of those. Now, over here, I've got 2 hydrogens, which was this one and this one. But because I needed 2 hydrogens, I also need 2 OHs. So I need to put a 2 here, which would also mean that I'd need a 2 here. But don't worry about balancing the equation right now. We will do a lot of that in chapter 5. I just wanted to show you what was going on there. So what happens here is it not only creates a basic solution, or alkaline or alkali solution, but it also creates hydrogen gas. Now, what's the problem with creating hydrogen gas? It's flammable. And not only does this reaction create a flammable gas, but it also gives off a lot of heat. So you have flammable gas and heat, and it's now obvious why we're getting this when we have this reaction, because you get a lot of combustion of your H2, okay? All right, so that's what happens with our alkali metals. Now we're moving on to group 2 or 2A. And these are our alkaline or alkali earth metals. And they are the group right next to our alkali metals. So if we back up here, we've got our alkali earth metals. See, beryllium, magnesium, calcium, strontium, etc. Now, these aren't as reactive as our alkali metals, but they're still pretty reactive and they still make our solution basic. Now, if we look over here, we can see that we've got our alkali earth metal calcium in rholeids there. And why would we want that? Well, right here, it says that they tend to make basic solutions when dissolved in water. So if you've got heartburn, and that's caused by acid in your stomach, if you put some base in there, the acid and base will do what? They'll neutralize. And neutralizing your stomach acid is really good if you've got stomach acid shooting up into your esophagus and burning you, which tends to happen to me on Friday nights because I like to go and get some cheese enchiladas. And it gives me heartburn every time. And I say to myself every time that I'm not going to do that again. But enchiladas are so good that I do it to myself again. Okay, so magnesium and strontium are over here, and these are used in fireworks. Magnesium gives a bright white glow, and you're going to see this in physical and chemical changes, that lab in your lab. And strontium gives a lovely red glow. So that's where in real life we'll see our alkali earth metals. So again, you guys, we've got our alkali metals here in this column, and then we have our alkali earth metals in group 2 or group 2A, depending on how we label our periodic table. Okay, that brings us to the transition metals that are in the center. So we have groups 3 through 12 here, if we're going with the 1 through 18 labeling. And we have the B's in there if you're going with the other labeling. So groups 3 through 12, and these tend to have high densities and high boiling points. So all of these are metals, and they're often used for electrical conduction. And if we take a look right here, we can see that we've got copper. This is the most famous one used for electrical conductivity. And the others that are really good at conducting electricity are right here, silver and gold. But what's the problem if we put silver or gold in our wires? It's expensive. Yeah, so most of us don't have gold wiring in our house. So good conductors there, and these atoms or these elements tend to have vivid colors when they're in compounds and they're made into solutions, which means that compounds of transition metals put into water are often lovely colors, and they're often used as pigments. So if we take a look at this, you can see the different colors here. So zinc compounds tend to be clear or white. So if you think of the summer, if you're trying to not get a sunburn on your nose and you put zinc oxide on your nose, if it's not dyed a different color, it's just naturally white. Copper here. A solution of copper 2 sulfate is definitely something that most introductory students will see in the lab. And you'll not only see it once, you usually see it about 3 or 4 times. Copper 2 sulfate is a blue solid, and if we dissolve it into water, it makes a blue solution. And then you can see nickel compounds tend to be green and cobalt, a pink red color, and then iron tends to be an orangey red color. And that makes sense when we think of the color of blood. We've got iron in our blood, in our red blood cells. And that brings us to the next group, the lanthanides. Now the lanthanides are down here, right here where it says lanthanide series. So if we look at the periodic table, we can see that it goes 1, 2, 3, 4, blah, 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 all the way to 10, and it keeps going. And if we get all the way down here, we'll notice that we have 55, 56, and then all of a sudden it goes, woo, 57, 58, all the way to 71, and then it comes back up here to 72. So the lanthanides are right there. So sometimes they're called the inner transition metals because they're squished in there. Now, why is it like that and not spread out? Well, that would take a lot of room on the periodic table if we swished our lanthanides in the center right there. So what we do is we take them out and we put them down here. Okay, so back to the lanthanides. These are elements of 57 through 71, so lanthanum to lutetium. And how do we use these? Where do we see these? Well, they're commonly used in lasers, and they're often put on sunglasses to deflect UV and infrared rays. They're also used in superconductors and in hybrid and all-electric cars, usually in the batteries or magnets in these cars. And these guys aren't very exciting. They just look like some gray or silver shiny rocks. You guys can see them all down here. Now, back to where they are on the periodic table. Notice how I said lanthanum starts those off? Well, lanthanum is right here. And it is technically right here on the periodic table. And the lanthanide series gets its name from lanthanum. So sometimes lanthanum is included in the lanthanides and sometimes it is not. So if you notice 57 through 71, that gives us 15 elements. A lot of times the lanthanides will start from 58 and go to 71. Don't worry about that too much, okay? Just realize that we've got 57 right here all the way through 58, and then it comes back up right there, okay? All right, switching back to blue ink. And that's moving us on to the actinides or the actinoids. Now, I have never heard anyone call these the actinoids, but apparently that's an alternative name to actinides. And this set is elements 89 through 103, so that's actinium through lawrencium. And actinium is the very first element in this series, and it is right here. And if we look back here, let me change colors. Actinium is right here, and it has the same issues that lawrencium has. So let me erase some stuff up here. There we go. So actinium is actually right here. So it goes 88 and then 89, and then we come down here. So this guy's really up there. And then we come down here to 90, and we go wee all the way to 103, and then we go back to 104. So sometimes actinium is included in the actinide series, and sometimes it's not. We just say, oh, well, the actinide series is named after actinium. So just be aware of that, okay? All right, so about the actinides, only actinium, thorium, and uranium occur naturally. All of the other elements that are in the actinide series, all of these down here, besides the ones that I just mentioned, are synthetic, and they are created by bombarding a heavy element with neutrons or alpha particles, or they result from some kind of radio decay. Okay. Now, these ones are radioactive, so all of our actinides are radioactive, and that's what's special about the actinides. The one that we have heard about the most is probably uranium in terms of nuclear power and politics and all of that stuff. Now, moving to the right in the periodic table, we have groups 13 through 16. So that is also called 3A through 6A. It's all of these in here. Those ones in there don't really have a common name like alkali metal or alkali earth metal or transition metals. These contain elements that are abundant in the Earth's crust, like carbon and oxygen, and in the atmosphere and in living things. And you have probably heard that we are carbon-based life forms. And there we go, carbon is right there. These groups, this group here, right here, 13 through 16, this contains the metalloids, and we just talked about the metalloids. And they're these guys in here. Now, look at this one. This chart right here included polonium, but it did not include astatine. So you can see how one periodic table included one and the other one included the other. So again, just keep in mind that sometimes polonium and astatine are left out and sometimes they're put in there. Okay, so if we take a look at this chart right here, it's going to show you the relative abundance of elements in our universe. And if you look over on the left-hand side, you'll see that helium and hydrogen are the most abundant. And that makes sense if you think about what stars are made of, which is what? Helium and hydrogen, and those are some pretty big blobs in our universe, those stars. All right, moving on to halogens. Halogens are group 17, which is also called group 7A, and those are these guys right here. So we've got fluorine, chlorine, bromine, and iodine. I don't know why it's iodine and not iodine, but some professors will say iodine. So that actually makes more sense, but Americans say iodine. Alrighty, so backing up, what do halogens like to do? Well, they love to form salts. And sodium chloride, which is table salt or salt that we use in the kitchen for cooking or for shaking all over our fries, because how do you have fries without salt? Yum, 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 yum. Salts are, in chemistry, a metal and a non-metal. And remember, in chemistry, sodium's not the same as sodium chloride. So sodium is a metal and chlorine is a non-metal. And don't worry about the change in the ending from chlorine to chloride. We'll talk about that later. But when you have a metal and a non-metal together, you're forming something called a salt. So potassium is a metal and bromine is a non-metal. Now potassium, you probably think, how is potassium a metal? That's something I eat in my bananas. Well, when we're talking about classification of the periodic table and potassium on its own, it is a metal. Okay, so anyways, halogens love to form salts with metals. So you'll notice here we have a chlorine, here we have a bromine, and here we have chlorine again. So they love to get together with metals. And when halogens are on their own, they like to be in the form of a diatomic molecule. Now, di means what? Di means two, and atomic means what? Atom. So they like to be in the form of two atoms together. So we have F2Cl2 and Br2 down here. And chlorines, they like to exist naturally as two chlorines bond together. And our bromines like to do the same thing, and our fluorines also like to do the same thing. If we look over to the left, we can see bromine and we can see iodine. If we had chlorine, we would see that chlorine was a green gas, and in one of your labs, you will see that. Okay, moving on to noble gases. So noble gases are group 18 or 8A, and those are right here. So we've got helium, neon, argon, krypton, xenon, radon, and ooh, right there, okay? These are very unreactive, and they don't like to bond to other molecules or, other atoms like halogens do. So we said halogens love to find a metal to bond to. Well, noble gases, they don't like to do that, and that's where they got their name. So people who are of the nobility class, they tend to not like to interact with the common folk. So the noble gases got their name from that class of people because they don't like to interact with the other elements. They just like to be on their own and not say hi or not do any barbecues or anything like that. Okay, so what we have in this group are some elements that are common to us, like neon. We're really used to neon signs. And helium, we put helium in balloons, and it's less dense than regular air, so it floats. Also, radon. Radon is a radioactive gas, and it is the #1 source of lung cancer for non-smokers. So this is why if you are in an area that naturally has radon in the ground, like Portland, Oregon, often when you buy a house, you'll ask for a radon a test to see if there's radon in the house. And if there is, they've got to do some radon mitigation, which costs a lot of money. So if you're selling your house, you're crossing your fingers that the test is clear. Okay, so that is the parts of the periodic table in terms of physical characteristics and electronic properties. And next we'll talk about diatomic molecules and some electron configurations and allotropes. But that's it for this lecture. I will see you next time. Bye-bye.